Good morning, my dear students. I am your faculty, Dr. M.Bala Theja. In previous videos, we have discussed about the topics of beams, derivation of the shape functions of the beams, derivation of the stiffness matrix of the beams. Now, we will concentrate about the analysis of the beams, that is beams problems. See here, the problem is look like a beam is fixed at one end and supported by a roller at the other end. Has a 20 kilonewtons concentrated load applied at the center of the span as shown in figure. Calculate the deflection under the load, construct and shear force and bending moment diagrams for the beam. So here a beam has taken, one end is fixed, other end is supported by the roller. 20 kilonewtons are acting at the center of the beam. Okay, and after that, by using the analysis of the FEM analysis, we have to find the deflection and shear force and bending moment diagrams. See here, in this beams we are having the total length of the beam is 100 centimeters. Young's model is 20 into 10 power 6. Inertia is 2500 centimeters per 4. So you can observe here, this is the beam at the center, 20 kilonewtons are acting to downwards. So this is the problem has given. Corresponding this problem, we have to calculate the deflection and shear force and bending moment diagram. Now we will see the solving of the problem. So here this beam diagram I am taking as a free body diagram here. Okay, so here this beam is considered as a two element. This is the first element, this is the second element. So first element, second element. So first element, second element. The first element is having two nodes, that is first node, second node, first node, second node. Second element we are having two nodes, that is the second node, third node, second node, third node. You can remember important point here. In the beam we are having three nodes. Every node acts vertical displacement and slope, that is the rotation of the moment, and shear force, bending moment. The four parameters are acting at the particular node. Here the second node, the vertical displacement, rotation of the beam, that is the thing of slope, shear force, bending moment. So here vertical displacement, slope, shear force, bending moment. So every node has four parameters are acting in the particular node. So here if you observe here V1, F1, theta1, M1, these are the displacement, vertical displacement, shear force, slope, bending moment at node 1. This is the things at node 2. This is the things at node 3. So here first we would like to follow the stiffness matrix for the first element. So this is the first element. So first element of the beam, what is the formula? Stiffness matrix of the first element of the beam, that is direct formula K equals to EI by L cube 2L 6L minus 2L 6L 6L 4L square minus 6L 2L square minus 2L minus 6L 2L minus 6L 6L 2L square minus 6L 4L square. This is the formula for the first element, that is K1. Okay, here you have to substitute the E value 20 to 10 power 6 and 10 power 6 into 2500 by length is 500. First element of the stiffness matrix. So here L is substituted as a 500. Okay, now what will get the answer? So here stiffness matrix is the first element 400. When we have to substitute that value, we'll get 400. Remaining everywhere we have to substitute the 500, then we'll get answer is this matrix. So 12, 3000 minus 12, 3000, like that we are getting the matrix. So this is the first element now. So V1 theta 1, V2 theta 2 are acting. So same thing here also, V1 theta 1, V2 theta 2, V1 theta 1, V2 theta 2. For the second element of the stiffness matrix, we want to find the stiffness matrix of the second element. This is the second element. So what is the stiffness matrix of second element? So K suffix 2, EI by L cube, this formula. EI by L cube into this formula. So here stiffness matrix second element, EI by L cube nothing but 400. So here we have to substitute the L value. Here also we have to substitute the L value 500 from this formula. Then we'll get, this is the matrix. So 12, 3000 minus 12, 3000. Same formula. Okay. Same matrix here also. Now, in the second element, we are having here V2 theta 2, V3 theta 3. Same here also V2 theta 2, V3 theta 3. V2 theta 2, V3 theta 3. Then we have to assemble the elements, that is first element stiffness matrix, second element as stiffness matrix, that is K1 plus K2. So here in the stiffness, assembling of the stiffness matrix, so complete beam of the stiffness matrix. So here how many displacements are acting? V1, theta 1, V2, theta 2, V3, theta 3. So that's why V1, theta 1, V2, theta 2, V3, theta 3, V1, theta 1, V2, theta 2, V3, theta 3. Now see here, V1, V1. What is the value V1, V1? 12. I am writing, I have written, sorry. Theta 1, V1, that is 3000. Theta 1, V1, 3000. V2, V1. So V2, V1, how much? Minus 2, 1. Theta 2, V1, how much? Theta 2, V1, 3000. V3, V1. So V3, we don't have V1. So we don't have V1. V3, V1. Na? V3 we have, V1 we don't have. So that's why 0. Theta 3, V1. So V1 we don't have. So that's why 0. So again V1, theta 1. V1, theta 1. That is 3000. Theta 1, theta 1. So theta 1, 10 power 6. V2, theta 1. V2, theta 1 minus 3000. Theta 2, theta 1. So theta 2, theta 1. That is 5 into 10 power 5. V3, theta 1. So V3, theta 1. We don't have theta 1. So 0. Theta 3, theta 1. We don't have 0. So that is 0. You can observe here also. V1, V2. How much V1, V2? So minus 12. And theta 1, V2. How much? Theta 1, V2. That is minus 3000. So V2, V2. You can observe here. V2, V2 minus 3000. And V2, V2. Again 12. So you can observe here. V2, V2. What is the value of V2, V2? V2, V2, 12. Here also V2, V2, 12. So total 12 plus 12, 24. That is you can write. Theta 2, V2. So theta 2, V2 minus 3000, minus 3000. Again here also theta 2, theta 2. That is 10 power 6. Sorry, theta 2. How much? Theta 2, V2. So theta 2, V2. That is 3000. Again V3, V2. So V3, V2. How much? Minus 2, 1. Again theta 3, V2. So theta 3, V2. That is 3000. So corresponding to this, you can calculate complete matrix. Okay, right. Then, so first we have find the stiffness matrix of the first element. Stiffness by first element. This is stiffness by second element. After that we have to assemble. Then we have to apply the finite element equation, that is F equal to K into U. So what this is F nothing but. So here F matrix equal to stiffness matrix into displacement matrix. So here F matrix, that is, this is the forces. Okay. So forces, what are the forces that are acting in the particular nodes? In the one node F1, M1, F2, M2, F3, M3. So F1, M1, F2, M2, F3, M3. So this is the stiffness matrix of that's assembling of the stiffness matrix. Complete this one. And again U, displacement. What are the displacements we have? So V1 theta 1, V2 theta 2, V3 theta 3. V1 theta 1, V2 theta 2, V3 theta 3. You can know. Now you have to apply the boundary conditions. Very important thing. You have to apply the boundary condition. So here F1, M1. Here you can observe here F2. F2 value how much? F2 value 20 kilonewtons are acting now. So here the 20 kilonewtons are acting at particular to downward direction, F2 acting. So here, so that is the thing I am taking consider as a minus 20,000. So that is I am considering as a minus 20,000. Now you can observe the boundary conditions. What are the boundary conditions we have? This is important point. This diagram you can observe. In the particular node, here V1 vertical displacement and slope will be 0. Why? It is the fixed. That is you can remember. V1 theta 1 will be 0. And again switch to second node. Here the thing what I am telling that the V2 vertical displacement of the second node and slope theta 2. Okay. So here you can observe the important thing is here the thing is I am telling that V1 theta 1 will be 0. Here F2 will be acting downward, but M2 will be 0. Why? We don't have any roller movement here. So that's why M2 will be 0. That is the boundary condition. Now switch to third element. In third element also roller support we have. So that's why V3 will be 0 and M3 will be 0. So these are the boundary condition. So you can remember what I'm telling the boundary conditions. You can remember that is the fixed now. So V1 equal to 0, theta 1 equal to 0. Here only force will be acting, no roller momentum. So M2 will be 0. Here here roller moment is there, but the force doesn't acting here, so that's why V3 and M3 will be 0. So these are the boundary condition we have to substitute here. So what is the boundary condition? V1 theta 1. So first element fixed now, so 0. Second element V2 theta 2. Okay, and third element, in the second element only M2 will be 0. Okay, in the third element theta 3 is there, but V3 will be 0. Okay, that is I have told that. Okay, so again in the second node M2 will be 0 and third node M3 will be 0. Okay, I have given the complete boundary condition. Now you have to observe the thing what I'm telling, that when it is 0 na, the complete, this is the first 0, so first row first column will be cancelled, and second 0 na, second row second column will be cancelled, and fifth 0 na, so fifth 0 fifth row fifth column will be cancelled. So what we have, minus 20,000 0 and 0, and remaining portion we have, so that is we have to write here minus 20 to 10 cube 0 0 equal to 400. So these are the cancel now. So what we have here, 24 0 3000, 24 0 3000. Next 0 2 into 10 power 6 5 into 10 power 5. Okay, next fifth row 3000 5 into 10 power 5 10 power 6, right? Then what we have, so this will be 0, this will be 0, this will have V2 theta 2 theta 3 is writing here. Now I have to apply the equation. So here first equation, this matrix form is conversion into equation form. Minus 20 into 10 cube equals to 400. So here first row first column, 24 into V2, 0 into theta 2 0, 3000 into theta 2, 3000 into theta 3, that is the first equation. Second equation, so 0 equals to 400 first row second row first column, 0 into V2 0, 2 into 10 power 6 into theta 2, 2 into 10 power 10 into theta 2, 5 into 10 power 5 into theta 3, and third 0, again here you can observe here 400, so third row third column, 3000 into V2 and 5 into 10 power 5 into theta 2 and 10 power 6 into theta 3. Solving about these equations by using calci and solving the equations, mathematical solving the equation, otherwise calci you have to use, you have to give the constant of these numbers, then we'll get easily this solution, that is V2 theta 2 theta 3. By using the calci you have to do this calculations. Okay, now we have to find the we have to get here complete displacements of the problem. Now we have to find the shear force and bending moment. So now first shear forces, what are the forces we have here? So F1 M1 F2 M2 F3 M3. So shear force F1 F2 already has given, so F1 F3 we have to find that. Okay, and M1 M1 M2 M3 we have to find, so that is the thing we have to find here. So this is the first F1, I want F1, so this is the F1. So here when you have to find the F1 value, what you have to do means, you can observe when the F1 value you have to find, that shear force you have to find, you have to multiply this row matrix and column matrix. So 12 into 0 0, 3000 into 0 0, minus 12 into V2 minus 12 V2, so minus 12 V2. Okay, and 3000 into theta 2, 3000 into theta 2. Okay, and 0 into 0 0 0 into something theta 3 0. So this is the shear force value. Here F1 value for 400 minus 12. What is the V2 value? Minus 3.645 plus 3000. Theta 2 value how much? Minus 0.03. Then we'll get 13,050 newtons. Now M1 value. We have to find the M1 value now. So what is M1 value? This is M1 value. 3000 into 0 0 and plus 10 power 6 into 0 0 minus 3000 into V2 minus 3000 into V2 minus 3000 into V2. Okay, this 400. Okay, minus 1000 into 2, again 5 into 10 power 5 into theta 2, 5 into 10 power 5 into theta 2. Okay, 0 into something 0, 0 into something 0. So this is the equation. So you have to substitute the value V2 here, minus 3.645. You have to substitute the value of theta 2, so this is the value, then we'll get this answer M1. Again F3 value, so this is the F3 value, This is the row, this is the column. 0 into 0, 0, 0 into 0, 0, minus 12 into V2, minus 12 V2, minus 3000 theta 2, 12 into 0, minus 3000 into theta 3. Same thing. 400 minus 12 V2 minus 3002 minus 3. We'll get this answer. This is F1, M1, F3. Okay. So here you can observe here one important point I am telling that. In the shear forces, what are the values we have? F1 is here, and F2 has given, and F3 we got it. So by this equation we have to do the shear force diagram. So here this is the beam length. Shear for 13,750 positive now, so 13,750, and F2 value minus 20,000. So from to here minus 20,000. Again F3 6,250. So here whatever the value you got here, that will be added towards to the 0. So that is the 6,250 newtons value. So this is the shear force diagram. This is the shear force diagram. And same the bending moment. So bending, this is the moment. So M1 we have to find it, and again M2 and M3 it will be 0. Okay, so there is no moment, and there is no moment at the third element, there is no moment on the second element, so it will be 0. At the first element we have 37,000 so 3750 200 Newton centimeter. So this is positive now, so positive, again 0 now, so it will be comes to here. So that is the thing, again 0. So this is the thing of bending moment diagram. Okay, this is the bending moment diagram. This is the complete video of the beam analysis of the beam. So here we got shear force diagram, here we got bending moment diagram. Okay, right. So one more important point I am telling, that the overview of the problem. Whenever the problem has given, at the time you have to take the free body diagram, you have to apply the 4 parameters particular nodes, then you have to apply, you have to divide the elements, first element, second element, every element you have to find the stiffness matrix. This is the first element stiffness matrix, second element stiffness matrix, and you have to second element stiffness matrix, you have to assembling the stiffness matrix, then you have to apply the finite element equation F equal to Ku, then you have to apply here boundary condition. Okay, here you have to apply the boundary conditions. After that you have to get the matrix, this matrix conversion into equation form, this equation, by this equation, so we have to solve, then we'll get the then we'll get the displacements. Okay, displacement you will get, and after that by this matrix easily you have to find the shear force and bending moments values, then you have to draw shear force and bending moment diagram. So this is the complete information of the analysis of the beam, that is the beam problems. Okay, I think everyone has understand. Okay, so thank you so much, all the best. I think the entire beams chapter has finished. One more important point things, in the frames we have the syllabus in this chapter, but in the frames we don't get any problems, any theory also. But even though frames is very easy, you have to observe same formulas, same derivations, same similar, that some notation will be changes in the frames. So suppose we have to example here, this is the matrix. In the frames you have to observe, we are getting only this much matrix only. Okay, that is the thing only frames. So it is similar to beams only. Okay, you don't worry about that. Finally what I'm telling, that this is the complete second chapter I have finished it today. Okay, tomorrow on the next videos onwards I will take third chapter. Okay, all the best to everybody. Thank you.